Hey everyone, in this video we're going to solve for the inlet throat diameter of the gigantic GE90 Turbofan engine that powers the Boeing 777. So what exactly am I talking about when I say the inlet throat diameter? If you look at any turbofan engine on a civil aviation aircraft, you'll note that the big fan is actually recessed back into something called the nacelle, which is essentially the outer casing of the engine. So if we're talking about components of the engine, the part from the front plane of the nacelle back to the front of the fan is called an inlet or diffuser. If you look carefully at an engine, you'll see that the nacelle actually widens out from the front plane back to the fan. We'd like to solve for the minimum diameter or throat diameter at the front of the nacelle. I'll go into more detail about design of diffusers in another video, but it's an extremely important component that often gets overlooked because of its apparent simplicity to the untrained eye. I'll be analyzing the diffuser during cruise, which is sometimes called on design because that's where the aircraft spends most of its time. The Boeing 777 cruises at a Mach number of about 0.85. Bad things can happen if the air is still at Mach 0.85 when it reaches the fan, so the goal of the diffuser is to slow down the incoming air to a lower Mach number, somewhere between about 0.4 and 0.7. In my calculations, I'll assume the air is slowed to Mach 0.6. We'll be using concepts such as the conservation of mass, speed of sound, isentropic relations, and the ideal gas law. If you don't know what some of those mean, don't worry because I'll walk you through it. At the end, we will be able to compare the answer we obtained to some measurements from this really cool picture, and I'd like to thank photographer Ron Stella for giving me permission to use this photo in this video. And with that, let's get started. So here's the side view of the inlet in black. You can see that the area is smaller here, and then it goes out to a bigger area at the back. This is the free stream flow coming in from the front with this large arrow, and then here is where the fan is. And you can see there's a smaller arrow representing that there's a smaller velocity at the fan than at the inlet. I'm labeling state 1 as the inlet and state 2 as the fan, or the exit of the inlet. So we can say that our Mach number at state 1 is 0.85, that's our cruise Mach number, and the Mach number at 2, which is the fan, or exit of the inlet, is 0.6. I'm assuming an altitude or cruising altitude of 35,000 feet, which is 10,668 meters. And I'm also assuming that the diameter of the fan, as quoted online at different sources, for the GE90 115 is 128 inches. I'm assuming that the ratio of the specific heats, gamma, is 1.4 for air, and that the specific gas constant for air is 287 joules per kilogram Kelvin. Here are the general steps for how we're going to go through the problem. We're going to start with the 1D conservation of mass equation that's going to relate densities, velocities, and areas between state 1 and state 2. Then we'll solve for the static pressure and temperature in the free stream, so P1 and T1. Using T1 and the definition of Mach number and the speed of sound, we'll be able to find the flight velocity U1. Then we'll be able to find the static pressure and temperature at the diffuser exit, or at the fan, using stagnation pressures and temperatures from state 1 and state 2. Then we'll find the diffuser exit velocity using the static temperature from state 2. And then we'll solve for the throat diameter using the conservation of mass equation. So here I'm going to quickly derive the 1D conservation of mass equation. It's almost a quasi-1D because the areas are allowed to change. So I'm going to start off with the side view of the diffuser in black, and I'm drawing a control volume in these red dashed lines, so you can see the flow coming in at a velocity u1, leaving at a velocity u2, and by definition we draw the surface normals of this control volume outward on both sides. So you can see the normal n1 hat is out to the left on the inlet, and the outlet n2 hat is out that way. So the general conservation of mass equation is here, shown here. So it's equal to the time rate, so ddt, the time rate of change of the mass inside the control volume. That's this. When you integrate the density over the volume, you end up getting the mass in the control volume. And then it's the time rate of change of the mass in the control volume plus what's happening at the boundaries of this control volume. So what's going out, what's coming in, and that's what this term is for. And so it's saying that the time rate of change of mass in the control volume, if it's increasing, it's balanced by this inflow and outflow. So we don't have to worry about the time rate of change because we're assuming a steady flow. In this case, we're saying that all the mass that's coming in is leaving. So we can get rid of this, say that's 0, and we're left with just this term here, which is the integral over the surfaces. So we're integrating over this surface here and this surface here, the density, and multiplied by the velocity dotted with the surface area here.
okay, and that's equal to 0. So I'm going to just split this integral up into two different integrals. The first one's going to be an integral over the inlet, and the second is going to be the integral over the outlet. And that's why I have this double integral over the inlet, state 1, outlet, state 2. And the inlet velocity is u1 going in this way, and we can split up this ds vector into the n hat and then just a scalar differential area. So that's why I split it up into this here. So I'm dotting the u1 velocity with the normal vector on that control surface, and then I'm multiplying it by the differential area, and we're integrating over that area. So that's what this double integral is. We're integrating over the area. And then same goes for the outlet here, where we have, again, the outlet velocity u2 dotted with the surface normal n hat 2, and then integrating over the full exit area, and this is equal to 0. And so based off of the dot product, if the velocity vector is in the same direction as the normal vector, if you take the dot product of those two, you'll get 1. And if you see in this case where it's opposite, you have the u1 going in and the normal vector coming out, then you get a negative 1. So you get a negative value when they're opposite directions, you get a positive value when they're in the same direction. So that's why this becomes negative in this equation here. So you get negative rho 1 u1 a1, and then here it's plus, so plus and a positive, plus rho 2 u2 a2 is still equal to 0. And then we get the final form that we want, which is the density times the velocity times the area at the inlet is equal to the density times the velocity times the area at the exit. And we cannot say that the densities are equal because we are dealing with compressible flow, because the Mach number is greater than approximately 0.3. So we're up in the range where we're considering compressible flow. All right, let's take a look at the units in this equation. So we have the rho UA from the previous slide, and if we look at the units of density, it's in kilograms per meter cubed. For velocity, it's in meters per second, and for area, it's in meters squared. So if you look at this, the meter squared times meter, that's meters cubed, cancels with this meter cubed, and we end up with kilograms per second, which is what's over here. And we can denote this by the symbol m dot down here. And m dot is the definition of the mass flow rate. So it's a mass per unit time. And so another way of writing the 1D continuity equation that we're going to use is m dot 1 is equal to m dot 2, which is just saying that the mass flow rate at the inlet is the same as the mass flow rate at the outlet, and it's constant. The next step is to find the static temperature and pressure of the free stream, or of the inlet of the diffuser. So if you recall, I said the altitude that we're flying at is 35,000 feet or 10,668 meters. And from my thermodynamics book, in one of the tables, table A16 in my particular book, it has the table of temperatures and pressures for different altitudes. And so the temperature at this altitude is 221.05 Kelvin, which is approximately negative 52 degrees Celsius. And the pressure is 24,129 pascals. So we'll use this to find the speed of sound and thus the velocity. Okay, now let's solve for the flight velocity. We'll start with the equation of Mach number equal to the velocity, the flight velocity, over the local speed of sound. So you can see that if you are flying faster than the speed of sound, then your Mach number is going to be greater than 1. If you're flying below the speed of sound, your Mach number is going to be less than 1. If we rearrange this, we can put the velocity over here, and we can see that the velocity is equal to the speed of sound times the Mach number. Definition's right here. So first we want to solve for the speed of sound, because we're trying to find the flight velocity, and we already have the Mach number. So for an ideal gas, which we've assumed, and we can assume that at altitude we have an ideal gas, we can say that A1 is equal to the square root of gamma R T1. And you can recall that T1 we have from the previous board because we solved for it, or we looked it up in a table. And so we can plug in our ratio specific heats, our specific gas constant, and that temperature, take the square root after multiplying them, and you get that the local speed of sound is 298 meters per second. So you'll note that this is actually less than the speed of sound down here at sea level, which is usually about 340 meters per second. And you can see that's probably, or definitely, because the temperature T1 has decreased, and so that decreases the speed of sound. So if we solve for the flight velocity, U1 is equal to A1 times M1, 298 meters per second times 0.85, we get that the flight velocity at the inlet of the diffuser is 253.32 meters per second. The next thing I said that we needed for our analysis are these things called stagnation properties, and they are denoted with the subscript 0. So when I say to say like T01, so T01 or P01, P01, both ways are fine, but they're stagnation properties, and it's what happens if you take this fluid element that's flowing, and if you take it and you isentropically bring it to rest so that it has no more velocity anymore, and it's the conditions that would occur if you brought it to rest isentropically. And by isentropically I mean reversible and adiabatic. Reversible meaning there's no losses such as friction or shocks, and the adiabatic portion is that there's no heat transfer, no heat loss or gain. So these are the formulas for the stagnation to static. So stagnation to static temperature, stagnation to static pressure. And I'll post a link here to a derivation video once I get around to it. But you'll just have to take my word for it right now. You can find it at any compressible flow book or thermal book. And so it's only a function of the Mach number, the ratio of the specific heats, and the static property. So you can see here, that's the case, here, that's the case. So if we are trying to find T01, the stagnation temperature at state 1, then we can just bring the T1 to the other side. So we have the 221 Kelvin times 1 plus 0.4, because we have 1.4 minus 1 over 2 times the Mach number, free stream Mach number is 0.85 squared, and we get that the stagnation temperature is 253 Kelvin. Which is higher than the static temperature, which is what we would assume looking at this equation, and what we would assume if we brought it to rest isentropically. And then in this case over here, we just have this added factor or exponent, gamma over gamma minus 1. And so we can plug in the static pressure, which is 24 kilopascals. Similarly here, raise it to the 3.5 power, and then we get 38.7 kilopascals. So right now you may be wondering why I introduced those stagnation properties, and if you take a look at the inlet here, there's two things that I haven't mentioned yet in the video, and it'll explain why we needed these stagnation properties. The first one is that we're assuming that the entire diffuser or inlet is adiabatic, meaning that there's no heat loss through the walls here, through the duct walls or the nacelle walls. And so this means that we can set the stagnation temperature at the inlet equal to the stagnation temperature at the outlet, which helps, as you'll see on the next whiteboard here. The second thing is that the stagnation pressure ratio is given as 0.95. So the stagnation pressure ratio is P02 over P01. So it's the stagnation pressure here at the exit over the stagnation pressure at the inlet. And you can see that it's a number that's less than 1, which means that the stagnation pressure here is less than the stagnation pressure here. And this is because we're going through a process that is not reversible. You'll note that I said it's adiabatic, but I didn't say reversible. If I had said reversible as well, it would have been isentropic, an ideal inlet. Here we're saying, okay, there's some losses due to friction on the walls, for example, and this is why we have a ratio that's less than 1 here, and it's denoted by, if you look in a lot of these propulsion books, it's denoted by this symbol pi sub d, which is the stagnation pressure ratio for the diffuser. And this particular number that I got is from one of these propulsion books. I'll put it in the description. The citation or the reference, and it's at a Mach number of 0.85, and there's a plot that has this pi d traced as a function of Mach number. So I picked Mach number 0.85 for a cruise and got 0.95 for a diffuser. And so let me just step back 1 second for the adiabatic assumption, and the reason you can assume it's adiabatic is because the heat loss depends on temperature gradient. So the temperature difference between, let's say, a point that's here and the point here. And if you look at it, we can assume that there's not really a big temperature difference between here and here, and so we can assume that there's no heat loss through this wall here. So that's why we can make this adiabatic assumption, but we can't make the reversible assumption because there's always going to be friction losses in here, maybe separation, that kind of stuff. So based off of what I just said, we can just say that the T01 is equal to T02, so T02 is 253 Kelvin. And then similarly here, we can say P02 over P01 is equal to 0.95. Just move P01 over here, which we know, multiply 0.95 by 38.7 kilopascals, and we get that the stagnation pressure at the exit of the diffuser is 37.76 kilopascals. So now that we have the stagnation temperature and the stagnation pressure at the exit of the diffuser, we can find the static temperature and the static pressure at the exit of the diffuser. And we're going to use the isentropic relations that we used before. These are the same ones as I wrote down before, but now I've substituted in the 1 for 2, 2, that's a 2, 2, 2, and 2. And you might be asking, well, you just said that the process is not isentropic, it's adiabatic. Why can we use the isentropic relations? And that's because you can always use the isentropic relations at a point in the flow. I can't say that I'm relating the stagnation pressure at 2 from the static pressure at 1, but I can say at a certain point you can always use these isentropic relations to get the stagnation to static pressure, temperature, density, whatever you want at a certain point in the flow. So that's why we can do it here. And so we're going to rearrange, and in this case, you can see that if we move the T to the other side, we have to bring this to the denominator, which is why we have the stagnation temperature on the numerator, this on the denominator. Note that we're using 0.6 now instead of the 0.85 from before. And when we solve the static temperature at 2, we get it to equal 236 Kelvin, which means that this diffusion process, this slowing down of the flow, has increased the temperature by a little bit. Same for the pressure. We bring this to this side, that to this side, and we get the static pressure at state 2 is 28.8 kilopascals. So in this case, we have a higher static pressure at the exit of the diffuser because if you have the faster velocity, you have a lower pressure, and then if you have a slower velocity, which is what we're doing, we're slowing down the flow, we have a higher pressure. Now that we have the static temperature, we can solve for the velocity at the exit of the diffuser or the fan. Same as before, U2 is equal to A2 times M2, speed of sound at 2, Mach number at 2. We can solve for the speed of sound for an ideal gas using this equation again. Square root of gamma RT2 now, static temperature, not stagnation temperature, 1.4 times 287 joules per kilogram Kelvin times 236 Kelvin. Take the square root and we get 307.94 meters per second. And if we plug that into this equation, times the Mach number now, we're talking about the Mach number at the exit of the diffuser, which is 0.6. We get an exit velocity of 184.76, and you can see that this has actually slowed down the flow as we thought it would. Okay, so let's write down the 1D continuity equation up here. Rho 1 U1 A1 is equal to rho 2 U2 A2. We just solve for U1 and U2, so we have those, so I put check marks. We still need the density at 1 and density at 2. This is what we're solving for, so this is what we want to solve for. So you can see we still need rho 1, rho 2, and A2. So A2 we can get from the measurement of the fan diameter. So I've said that the area at 2 is just pi d squared over 4. And the 128 inches is just 3.2512 meters. Put that in here and you get the area of the fan is 8.3 meters squared. So we can say, okay, we have A2 now. So let's get rho 1 and rho 2. Using the ideal gas law, we can write the pressure is equal to the density times the specific gas constant times the temperature. So if we rearrange it, we get the density is equal to P over RT. So we can do that for both rho 1 and rho 2 because we know the static pressure and static temperature at both of these states. So for rho 1, we plug the numbers in and we get a density of 0.3803 kilograms per meter cubed. And for state 2, we do the same and we get 0.4255 kilograms per meter cubed. And now we can say we have those as well, which means the only thing that we're left with is the area of the inlet that we're trying to solve for. So let's do that. So if we plug in to the mass flow rate equation for state 2, where we know everything, we can plug in the density, velocity, area, and we get a mass flow rate of 652.51 kilograms per second. And I've checked some data sheets online, and there's one that says that the mass flow rate is actually about 570 kilograms per second for this particular engine at cruise. And this could be because of what we chose, just all of the variables that we chose in the beginning, especially the compressor or the fan face Mach number, the 0.6 that I assumed it could be something different. I just assumed that it was right in the middle of that range. So that's where some of this error can occur in here, but we're going to assume that this is okay. It's not too far off. Then we're going to solve for the m.1 where we don't know a1 yet, so we get it in terms of this number times a1, and now we'll set them equal to each other. So setting both m.1 equal to m.2, we get this for the final solution of the inlet area, which is 6.773 meters squared. If we convert this to a diameter, we get 2.937 meters. Convert that to inches, and we get a diameter, inlet throat diameter of 115.6 inches, which is indeed smaller than the fan diameter of 128 inches. And so the question is, can we check this some way? And I have only found that the way to check this is online using the picture provided by Ron Stella, because I can't find the actual number anywhere, but I'd be interested to see if anybody could find that for me. But we can compare it now to that picture, so let's do that. So the way that I'm going to find the diameter from the image is to use pixel ratios, and based off of what I know from a document I found online. And so this is the front view of the engine that you'll see in the picture that I'll show in just a second. And what I measure in GIMP is the distance from the outer edge of the engine that you see, and that's going to be red, and it's going to be in pixels here. And then I'm going to measure from the throat, right where you see the throat stopping, and that'll be in green pixels. And I'm going to take that ratio, and I know that the outer edge that I'm measuring is the maximum nacelle diameter, and that is given in a document that I'll post in the description for airport handling of the Boeing 777 as 13 feet. And so that 13 feet is 156 inches. So then I have this equation where it's just a ratio saying the pixels over pixels is equal to 13 over something, the diameter that we're looking for. And so I just solve for that using the pixel ratio and what I know about the maximum nacelle diameter. So that's the way that I'll get this diameter from the picture, and we can compare to what I have, or what we just solved for.
Okay, so here's the picture opened up in GIMP. We're going to be using this tool over here, the measure tool, so you can press Shift-M or just click on this, and we'll be reading the pixels off down in the bottom down here. And so if you recall from the previous whiteboard, what we need from this picture is the maximum diameter, the pixels from the maximum diameter, and then also from the throat here. Okay, we're not talking about the inlet lip here to here. That's a different measurement. We're talking about the minimum diameter. So the first thing I'll get is the inlet. And so I'm going to take a point here, and you can see over here that you can actually see the tips of the fan blades, and that's because this picture is slightly off center, and also it has to do with just optical, just camera optics and stuff like that. So I'm going to try to take a point where we don't have the fan blade, we can't see the fan blades, and I think here down to here is probably a good place to do it. So I clicked a point here. I'm going to hold Shift, click again, and drag this down. I'm going to drag it through the center of this spinner here, okay, and then down to the bottom like that. So that way we know we're going through the center of the engine. And you can see that we're reading off 375 pixels. So I'm going to write down 375 pixels for my minimum pixel value. And now we need to get the maximum diameter pixel value. So here's it's a little bit trickier. Because you can see that the panels are actually a little bit off. They're probably doing some maintenance on the side of the engine here. So the panel here and the panel here, you can see, are detached from the actual engine. So it's hard to tell exactly where, but this is the best picture I could find. So we're going to try to just take something like this here. I'm going to Shift-click, drag it again through the center, and maybe up to about, let's see, we're going to be about there, okay? And then we're going to read that off, and that's 495.7. And if you recall, if you can go back to the other whiteboard, we do 495.7 divided by 375, and we get a value that's equal to 1.322, and that's the denominator of the equation. So we're going to solve for the D1, the diameter of the inlet, and that's going to be equal to our 156 inches, which is the 13 feet. That was my phone. Which is the 13 feet from the maximum, and then we're going to divide by that number, that ratio that we just calculated, which is 1.322, and if I do that, 156 divided by that answer, we get the inlet diameter is 118 inches, and that's not very far off from the 115.6, I believe, that we calculated from our calculations from before. So that's actually pretty cool, and this is a way that you can find, you can approximate. This is a rough approximation, but approximate some dimensions of engines that you might not be able to find online. So thanks for watching this demo, and I hope you enjoyed it.